Okay, good afternoon, everyone, and welcome to this special event, part of the discussion meeting on active matter and beyond. The ICTS INFOSYS Chandrasekhar lectures are a very special flagship lectures for us in the physical sciences. Typically, they are embedded as part of a program like this, and we invite eminent scientists to deliver these lectures. This is in the physical sciences. We have the Ramanujan lectures in the mathematical sciences and the Turing lectures in biology, computer science, and related areas. Since one of the purposes of this meeting is to felicitate Sriram, it's particularly appropriate that he should be giving these lectures as part of this discussion meeting. I'll now invite his student and ICTS faculty member Vijay to embarrass Sriram with an introduction.
We'll embarrass more on Friday, but today is the formal introduction. So it's an honor to introduce Sriram, of course. Sriram did his undergrad from Maryland, 77, and then got a PhD from Chicago in 83. Then did a couple of postdocs at the University of Pennsylvania and joined IISc in 86, where he has been ever since. In between, he had a short stint as the director of the TFR Hyderabad Center. Sriram is a master of the hydrodynamic approach, as many of us know very well, and he's one of the pioneering founders of the field of active matter, which we are celebrating, which studies collections of living systems, motile objects, and so on. For his work, Sriram is widely recognized, including the Bhatnagar Prize, the Infosys Prize, and also a fellowship of the Royal Society. So without further ado, we go ahead. So Rajesh.
So I'd like to invite Professor Jacques Proust, who's known Sriram for a long time, to present on behalf of ICTS a memento for these lectures.
So it's a great honor for me. Oops. It's a great honor for me to hand you this gift from prestigious ICTS. Thank you.
Thanks very much to ICTS and to Jacques. I don't know what to say.
It's a small sandalwood Buddha, so hopefully you'll like it.
I honestly don't know what to say. First, just thank you very much for inviting me. Thank you, so many friends who've actually shown up by traveling unreasonably long distances for this. I'm overwhelmed. Yes, as you can see, I don't know what to say. I sort of know how to give the talk, but everything before that, I'm in a bit of a state about. So I'm deeply grateful for grateful and a little anxious. I hope the Allure doesn't turn out to be bait and switch. But anyway, I think I've said lots of thanks. I'll just start. And in the course of the talk, I'll acknowledge various people who contributed. So one important point, I think, is that today's lecture is really not aimed at insiders in the active matter trade. It's really aimed at a broad physics audience. It is aimed at a physics audience. It's not sort of a generic public, very general public lecture. So if you like, it's aimed primarily at the students and postdocs in the audience. I have a feeling, and in particular, by the way, I should say, when I was asked to give these lectures, my immediate reaction was, wow, how wonderful. And I immediately said yes. And some days after that, I realized that 3 hours of 3 lectures, not 3 hours, 3 lectures of length, rather more than an hour, is a seriously daunting prospect. And that it's not realistic to expect me to present you 3+ hours of lectures on what I did over the past 3 months or 6 months. Inevitably, it's going to be a resume of sort of what I've been doing for about half my academic life. I realize also that, yeah, it's about half my academic life. So apologies to people who know these stories. I had no choice. Okay. With some luck, there are people in the audience who haven't heard this stuff before, or who haven't got this sort of overall view of it before, who will find this somewhat enlightening. So this first lecture is really going to be I'm going to try to make it a self-contained tour, mainly on early results, but then telling you sort of current updates on those early results. And there's more specific topics in the second and third lectures, in which I think more of it will be somewhat new, and some of it will be somewhat more offbeat. Okay, so today's lecture, I'll really begin with a leisurely introduction and background, and then in the active matter game, one fateful afternoon, some of us sat down and decided we're going to divide it up into dry and wet active matter, and that name has stuck. And I'll tell you a little bit about each. And under each of these topics, there's some subtopics, which I'm going to ad-lib a little bit and see how the time is going as we go along. All right. The second and third lectures, I will not bother you with the details about today. So maybe this is a better slide. Yeah. Does this work? Yeah. Okay. First, I should just tell you my current group, which consists of, at present, I guess, 4 grad students, 1 undergraduate, and a postdoc. Many of whom are working jointly with other colleagues. Some of these people are here. Recent alumni are in the pictures here, and these are alumni over the years. I'm not going to read out the list, but I really want to thank all of them from the bottom of my heart. It's been wonderful working with all of you. I don't have a similar slide on colleagues. Maybe I will in a subsequent lecture with colleagues and collaborators. Sporadically, I may have some photos in there, but anyway, this is who I've done the work with, apart from the other collaborators in the work. Okay, so again, to the students in the audience, and even you've probably heard this before, active particles are just particles that are powered in some way. The living cell, the cells in our body are active because they're equipped. They're supplied with nutrient, and they know how to take that nutrient and turn it into all kinds of systematic processes. Any system, any active particle takes free energy, converts it into work, and dissipates energy in doing so, and therefore possesses an arrow of time, permanently endowed as long as free energy is being supplied. And a collection of particles of this sort is, a collection of any kind of particles is a material, and we call such materials active matter or active materials. And of course, the reason we defined this category is so that we could just keep, yes? Okay. So we could just keep doing condensed matter physics by including living stuff also within that, broad and generous classification. Living tissue, groups of living organisms, individual components in those organisms, little mechanical or electrical or chemical imitations. All of these are different kinds of active particles. You can bunch them together and make weird kinds of active matter. You saw today in Yuk Shate's talk, for example, that just endowing particles with directional motion completely changed the game. It wasn't a very fancy or weird thing to do to those particles, but it was spectacularly game-changing. And this is why we actually think that introducing a little wrinkle into something we know really well, using the thing we know really well as a point of departure, it's worth exploring because a small input, a small investment turns out to result in quite remarkable effects. Okay. Again, I show this slide very often, but anyway, it's just to show the many kinds of synthetic active matter you can have, particles with some chemistry going on them, these and these. I think I have to show 1 or 2 movies here. And I don't know how to do it from the remote. So there's many examples, but let me show you. This, for instance, is just, you're looking top view at a surface that's vibrating up and down, and there's a little particle lying on it, and it's walking, okay? This is Nitin Kumar's, Vijay Narayan's, and then Nitin Kumar's PhD work. This is something that Vijay, who you saw up here a few seconds ago, did. He took two particles, connected them by a spring. This is a simulation. Gave them both random kicks, but made the mobility, that is the relation between force and velocity of one of the heads sensitive to the extension of the spring, but didn't make the noise recognize that fact. And he created an object which, purely by virtue of this asymmetry, would move. And then what he did was he alternated between a state where that asymmetry was built into the noise and the damping, so it is equilibrium, and now just wait, now broke that symmetry, and then it starts to move. This is the velocity distribution, which becomes centered at a non-zero value. This is the internal force distribution, which for an equilibrium system has to be 0, but for a thermal equilibrium system can be non-zero. That means in this non-equilibrium state, the internal spring force on average in steady state is non-zero. Okay? So this is work that Vijay, Madan, and I did, but really this is stuff that Vijay did. Okay? You can break thermal equilibrium in much more subtle ways. This again is that same vibrating surface, and there's particles lying on it. The particles have two ends which are kind of similar. In the ideal case, they're actually pretty much identical. And as a result, many of these particles you'll see are frantically moving back and forth with no particular sense of which way to go on average. Okay? Now, of course, the critical eye will find several particles which are actually more or less systematically motile, but a fair fraction of them, what they're doing is they've got more kinetic energy for moving like this, than for moving this way, which clearly you can't have in a system at thermal equilibrium, right? And so these are active particles without polarity. These are from the PhD work many years ago by Vijay Narayan. And then there's a variety of other examples. This is biofilaments and motors and ATP extracted from a cell. These are artificial motile particles from Ambarish Ghosh. And you could even imagine taking some two-dimensional electronic system and energizing it with some kind of, say, microwave power. And then the 2D physics of that system should be to the extent that that energy is taken up and dissipated, that 2D physics should be some kind of active matter physics. And that idea has actually been exploited by some groups also. So all of these are apart from living matter itself. The point is that, and the reason these are important, by the way, is that very often what you want is a system where you can control things reasonably well and change parameters and so forth. And for that, having an artificial active system is really nice. This is just to show that in a certain domain, it may be not that difficult to make a reasonably well-controlled active matter system. None of them necessarily have the spectacular degree of control that you saw in Zvonimir's experiments, for example, but they're pretty nice. Sorry, I should have mentioned names. I do have the names on there. Various people in the room have their names associated with various bits of this work. Yes. So, if you like, very crudely, what we're asking is, as physicists, that's a bunch of hard spheres. That's a bunch of hard spheres. This is a bunch of polymers. That's a bunch of polymers. And, when these are alive, the question is, in what way do these guys differ from these guys? How structurally, dynamically, and of course, you can't even ask the question about this one, but functionally, okay? So how is a bunch of beetles different from a bunch of hard spheres? How is a snake pit different from a polymer melt? That's roughly what we're after. And what can you do with them, okay? It's very important, yeah, one small point to make, and maybe I can just make it briefly on the board. Supposing I have a bunch of particles in vacuum, so, and that's some vector R, and there's some interaction potential V of R, and there's a bunch of such particles. In vacuum, and they interact with each other with a pair potential, okay? Imagine the same system now in a fluid background, okay? And imagine you could contrive to have exactly the same pair interaction, the same static pair potential between these cases. In one of them, these particles are moving around in such a way that their interactions conserve momentum. In the other, because there's a fluid background, the particles can lose momentum to the fluid or gain momentum to the fluid. At thermal equilibrium, these two systems have exactly the same phase diagram, okay? And you could take a third case. You could say, I'll take all of these guys and place them on a dry table. Okay, I'll adsorb them onto a solid surface. Again, under the condition that their pair potential is unchanged, all these three systems have the same phase diagram. Nothing can be different. Their dynamics may be different, their phase diagram will not be different. Once you are out of thermal equilibrium, in particular if you're active, it actually matters the dynamical ensemble you're living in. You know, is it a momentum conserving or a momentum not conserving ensemble? Actually can change the phase diagram. It can change it to the extent that in one setting a given phase could actually be stable and another could be not stable at all under any circumstances. Okay, so dynamical regimes matter infinitely. Okay, so therefore we found it useful to talk about wet and dry active matter. All right, you've been indoctrinated enough by this point, especially if you attended today's lessons, that you don't need to be convinced that you should care about this. Okay, but obviously, you know, we have a diverse range of reasons for being interested. Understanding the laws, incorporating these systems, you know, understanding how physics plays a role in living matter, and you know, being able to build something that does what these living things do, and at varying degrees of cleverness. So by the way, when should I stop talking? Oh, I've got that there. Okay. No, but I mean, I should leave how much time for questions? Huh? 20 minutes. All right. All right, so there we are. The problem itself, I mean, even if you take a fairly generous view of active matter, the problem actually has a long history, which I tried to assemble when I gave a talk on this at an occasion where several of the people in the room were present. Okay, from understanding ways in which a particle could propel itself electrophoretically by creating gradients along its surface, understanding the physics of fluids suffused with energy sources, treating the hydrodynamics of microbial swimmers, microbial or even macrobial, if you like, fish, as a problem in physics, computer simulations to imitate collective motion, the idea that collections of cells are a living example of liquid crystal physics. All of this is before the era that we conventionally call, you know, the beginning of active matter, which is essentially Vicek and Toner and Two's formulation of flocking theories. Okay, and around that time, you know, related problems like active membranes, motile polymers, cytoskeleton, all this is being discussed, and you know, it sort of went on. I won't read all this stuff out. What I wanted to emphasize was there's a fairly long prehistory, some of which was really way ahead of its time and therefore was ignored. Okay. Again, I'm listing these also because many of the people responsible for some of the fantastic developments in this field are actually right here in this room. So, you know, I hope all of you will get to talk to them and so forth. All right. One particular piece of work, you know, in the spirit of history of science, I wanted to highlight a little bit, which is a term that dominates discussions of the hydrodynamics of active fluids, namely the active stress. We thought we invented it. Okay? Well, turns out these guys, distinguished chemeng fluid mechanicians, had thought about all this a really long time ago. I mean, if you read the words here, you see they're completely on top of the problem. And you may remember at the end of Rahul Pandit's talk, those of you who were in the room, Rahul said, and this thing is called active model H, and Mike Cates and colleagues and so forth. Well, active model H really first appears in these guys' work. And it's exactly those terms. There's some composition field, some scalar field, a temperature or a composition, and you write down a stress bilinear in gradients of that object. It's in there. So these guys, so it's actually worth reading this. And these guys invite the community. Come on, folks, work on this. This is the greatest thing in the world. It is cited 42 times to date. And most of them are by papers by us or people we know. So you would think people would be a little more generous to these guys, at least now. But it's a very interesting paper, actually. And it is motivated by oscillatory phenomena in, sorry? Physarum polycephalum or something, yeah. Which is not a cellular slime mold, but a true slime mold or something like that. Yeah. And probably the reason it happened is our way of talking about messy, complex fluids. Just saying, look, we won't look at the details. We know how to write down the slow variables. It's a living liquid crystal, or it's a scalar field and a fluid flow and so forth. That really started a few years after this. Okay, so somehow the ground was not the soil was not ready for this thing to take root, and so really not much happened using it. Okay, let me just quickly tell you a few cool. I don't know, maybe skip a bit of this. One of the earliest examples of a sort of pure physics approach to self-propulsion, without even moving parts like flagella or fins or anything like that, was Mitchell is famous for I've forgotten the topic, something crucial in photosynthesis, except I'm not getting the name. Okay. Anyway, he got a Nobel Prize for it, so it's okay. He doesn't have to worry about me. Chemiosmosis, yeah. Suggested that maybe bacteria moved by maintaining an ionic gradient along their surface. It's a cool idea. It is one that's discussed also by friends, at least one of whom is in the room. J.L. Anderson discussing...
Can I say something?
Yes.
We try to do the experiments.
Yeah.
We try to do the experiments.
It's not on.
Okay, we try to do the experiments with vesicles for years.
I see.
But the way we imagined it was too difficult, so we failed.
I see.
And then a friend of mine, Joel Schnur, said we should use the platinum gold. And he was 10 years ahead of time, but he was at Naval Research, and he didn't get permission from the Navy.
I see. And the rest is history. I see. Yeah, again, this idea of something producing gradients along its own surface was talked about in this article by J.L. Anderson, but in practice, if you look at his actual calculation, he creates an external concentration gradient and drives it. And the people who really figured out how you could have a particle that creates a gradient on its own surface are Ramin and friends in much more recent time. And again, active processes were discussed by Pro and Bruinsma in the context of fluid membranes. Living cell membranes have all kinds of active processes going on in them. And they pointed out that if those active processes act like a sort of generalized force on the membrane, which could poke the membrane forward and could give rise to huge membrane fluctuations. We complicated the story by pointing out that the membrane acts back on the pumps. You get a different kind of dynamics and a different kind of statistics. I already mentioned microbial hydrodynamics. There's a long sort of time-honored tradition of fluid mechanicians studying organismal swimming, microbes as well as larger organisms. So these ideas were thought about and studied, but many of the features that are sort of stand at the center of the modern understanding of the active hydrodynamics of oriented fluids somehow were missed by these early workers. Okay. So that's general historical background. Now, the way I work, for example, when confronted by some new physical system, is not to look too hard at the details, but just pick what, by general understanding and by Ramin's talk, I think, yes, are the slow variables of that problem. And having decided on those slow variables, you ask, okay, if this system is in thermal equilibrium, I know what to do. If this system is permanently held in a state out of thermal equilibrium by internal energy conversion, what do I do? The idea is the following. Any internal energy conversion, if it is to have an effect on motions in directions that you're monitoring, can be viewed in this cartoon in the following way. That let this represent in an abstract way all the spatial variables in your system, okay? And for the time being, for simplicity, let's think of these as coordinate-like, not momentum-like, okay? So these are all time reversal even variables. Imagine you have some internal dynamics going on which is converting energy. In a chemical system, what does converting energy mean? It means taking some molecule in a high free energy state and degrading it in some way and using some of that energy. So this coordinate is how much fuel you have consumed, number of fuel molecules consumed. Or in those funny little experiments I showed you of vibrating surfaces, you can think of it as how many times the little plate has shaken up and down. Okay, so this is a running variable. That is, as the chemistry goes on, you're going up that way. Okay? Now imagine think of this as a hidden but physical direction. Okay? So as I said, by the way, this lecture is largely pedagogy, so I have to apologize to the experts in the room. Imagine in this abstract configuration space, you have what I've shown here as these grooves. They could be, these corrugations in that direction, or they could just be a more abstract thing, a mobility matrix, which connects velocities to forces. Velocity is mobility times force. Okay, and if this thing has a non-diagonal bit, then a force in one direction can give rise to motion in another direction, right? It means if you put a particle here, it'll roll in the grooves, right? So it's not even a metaphor, it's just a very simple retelling of chemomechanical coupling that allows devices to function. So apply a chemical force, get a spatial motion. Now, what we want to do is to formalize this and use this idea to build the dynamics of active systems. By the way, there's references strewn throughout the talk, but this picture really comes out of work by Frank, Armand, Jacques, understanding molecular motors, but has then been developed in various forms, including in a Langevin equation form by us recently. The idea is the following. So supposing imagine you've got three variables, Q, P. My commas are bad, okay. Imagine you have physical position and momentum Q and P, and this other coordinate X, okay? And right now imagine that everything is at thermal equilibrium, okay? So then there's some Hamiltonian H of P, Q, and X, temperature T, and what you have is a dynamics which consists of one part which is Hamiltonian, Q dot is del H over del P, P dot is minus del H over del Q. Now imagine these variables are a slightly coarse-grained description, so they're not the complete microscopic canonical variables. Imagine that P also has some kind of a Hamiltonian coupling to this other variable X, okay? And then X obviously will have a coupling to P with a coefficient of this sort, okay? Now imagine, so right now we're still talking equilibrium physics, okay? So there's a dissipative part of the dynamics which I put in here and here, right? This, I've treated X as a coordinate-like variable, so it has some mobility that comes in here. Each of these dissipative coefficients is accompanied by a noise. And what I've done is, I've said, supposing P and X have some kind of reversible mechanical coupling, then P dot will have something involving dH over dx, and X dot minus the same thing times dH over dP. And in general, nothing can rule out my allowing this off-diagonal piece of the coupling to depend on the physical coordinate Q, okay? So this is not a derivation of anything because I haven't told you where omega of q is coming from. I'm just telling you what it means for an energy conversion process to, in some invisible world, to affect the variables that you're looking at. Okay, essentially the idea. So you take an equation of motion like this. This is the chemomechanical coupling. You have these noises. You then ask, I want to study this system in a situation not where everybody is equilibrating, but where the variable x is subject to a fixed force. If x is a chemical coordinate, what that means is I keep topping up the reactant. I maintain the chemical potential difference between reactant and product so that that reactant keeps going in one direction. So that means I keep going up this way. So if I say, I'll just rename the force on the x coordinate, I'll call it delta mu for chemical potential difference. I keep it constant. So then if I only look at my variables p and q, I can of course look at the chemical variable if I want, but it will on average just keep increasing in time. If I look at p and q, then the off-diagonal coupling in my equation for p now acquires a piece which has, in principle, arbitrary dependencies on the physical variables. Okay, and again for simplicity, let's consider dependencies only on the variables q, the coordinate-like variables. All that they are constrained by are the spatial symmetries of the system. I break time reversal invariance by imposing a chemical driving force. So I endow the system with an arrow of time by going on pushing it in that one direction. I then acquire an equation of motion in which I've sort of acquired kind of infinite license to write down equations of motion in which terms of this quote unquote new terms in the equations of motion enter. The only thing I'm constrained by is if my system is isotropic, I better put down terms that are isotropic. If my system has some preferred direction, then I'm allowed to put down things in terms of that direction. So all I've really done by this elaborate exercise is to justify once and for all the writing down of kind of generic equations of motion, including terms that don't come from downhill motion in an energy function or Hamiltonian dynamics in an energy function. They come actually from an underlying Hamiltonian dynamics, but under circumstances in which some variable has been held constant. Some force has been held constant, okay? And this allows me, you can now sort of run riot. You can write down anything you like, okay? And I'm not going to, I want to illustrate this not because I'm going to now laboriously use it one after another for every system, just to inform you that you're free, you can actually do this. The next time somebody gives you an active system, you know how to write down its equation of motion. You can do that for many systems. One of the first systems for which we did it, now that ends the introductory part of the fundamentals part of my talk. I'm now going to talk about, actually this slide should have preceded this. I'm now going to talk about the first example. It's not super clear how many examples I'll get through. Let's take a very simple system. Remember I showed you those particles of Vijay Narayans which shuffled back and forth along their length? Supposing I wanted to write down a theory of the collective behavior of that system, how would I do it? Well, we asked ourselves that question just about 20 years ago. Aditi Simha, John Toner and I, and Shraddha and Aditi and I did some work on it later. So the ordered phase is an aligned phase, but it is defined by an axis and not by a vector, okay? So it's a uniaxial aligned phase. Structurally, it's the same phase as the liquid crystal in your computer. I forget. These days, do computer screens have liquid crystals or LEDs? I forgot. Okay. Yeah. Okay. This whole system is sitting on a substrate. So balancing the books as regards momentum is done by the substrate. You don't need to keep track of a momentum density as a slow variable. Okay. So the number of particles is conserved. So one of the slow variables is the concentration. The other slow variable, because the system is ordering, and so near the transition, the order parameter magnitude, and in the low temperature phase, the transverse fluctuations of the order parameter, the Nambu-Goldstone mode, are the variables you need to keep track of. So you need to just close your eyes and write down the equations of motion for a concentration and an orientation field, okay? You can do that using just the principle I told you, write down stuff that you're allowed to write down. The crucial thing that it turns out you end up being, that turns out to be, of the various things that you're allowed to do, the crucial thing turns out to be a particle current proportional to the divergence of the nematic order parameter. Okay. So the nematic order parameter is this tensor whose average tells you the local amount of anisotropy. A priori, nobody can tell me that I can't have a term like this, because if the order parameter is inhomogeneous, then even though the mean state has no sense of direction, when I splay or I bend it, I define a direction. Okay? This object and this object have a vectorial asymmetry. In the simplest case, oh, there should really be an n in front of that, sorry. This guy, you should argue on general symmetry grounds, system is out of equilibrium. There's an arrow pointing this way here, there's an arrow pointing that way there. There should be particle motion, there should be particle currents in a direction defined by that arrow. Okay? So, old hat, but I'm just reiterating it. So, this is seriously important because what it says is that that spatial variation in the broken symmetry mode enters at rather low order in gradients into the particle equation of motion. Okay? Now, the broken symmetry mode, remember this system, we are assuming it's condensed into an aligned phase. So long wavelength variations in that alignment are very soft. So if there's any noise in the system at all, they'll be excited abundantly and they relax slowly. Okay? What this story says is that they will contribute to mass motion. Okay? So you'll get, if you analyze this a little carefully, you will find that you will get a current that way proportional to the y derivative of the angle and a current this way proportional to the x derivative of the angle. Okay? The angle fluctuations, as I argued, are big because they are broken symmetry modes. And you can sort of imagine a steady state in which diffusive currents of order gradient of concentration and curvature-driven currents of order, again, one derivative on the angle are balanced. That means that in the steady state, concentration fluctuations are as big as broken symmetry fluctuations. Okay? And this is happening not because the order parameter itself is a velocity. The order parameter is a uniaxial tensor. So it's saying that curvature produces this current. So you predict enormous density fluctuations. So,
Is your noise Gaussian?
So in these, you could make it more complicated by putting in non-Gaussian noises or, so non-Gaussian noises are unlikely, okay, let me be a little careful, a little non-committal. Two things. One, you can ask, is the noise Gaussian or not? Two, is it white or not? Any noise with a finite time scale, you can sort of say that if you look on time scales long compared to it, modulo something that you may say in a moment. For many purposes, it's okay to look at time scales long compared to it and treat it as white. Not always, because some things could be non-zero for any non-zero correlation time or noise. Second, about Gaussian. In this family of systems, it's probably okay. There are probably systems in which over a biggish range of scales, you might worry about non-Gaussian effects. Usually what happens if you're looking at long wavelength physics, because you effectively incorporated many degrees of freedom, you don't need to worry about non-Gaussianness. But if you do this KMS kind of, there are these slightly fancier field theories where you worry about which I learned about from some friends of yours only recently. You could worry about non-Gaussian noise. It could become more and more important if you look at smaller and smaller scale fluctuations, because the number of effective degrees of freedom you'll be monitoring will be smaller. But if you're looking at long wavelengths, for the most part, it's okay to look at Gaussian. But that said, there are certainly situations in self-propelled suspensions, for example, where the motions are very non-Gaussian. So I'm staying away from that just now. So theory predicts an excess over root n in the number density fluctuations. Roughly speaking, experiments by Vijay Narayan and Narayan Menon saw these. The most reliable estimates of what's going on in these systems were from computer experiments by Sandrine Ngo and others, Yuk Chate and company, where they found number fluctuations bigger than square root n, but not order n. The linearized theory naively seemed to say n. Suraj and friends showed that one possible way out is that these fluctuations, the current depends on the divergence of the order parameter. This is a two-dimensional nematic. The order parameter itself goes down with scale. This at least weakens this square root delta n going as n a little bit because of that. It may not be the whole explanation. The reason I'm talking about this today actually is not for this, but for the story of topological defects. So conveniently as it happens, two topics that I'm going to talk about today have some resonance with some of the things that you talked about. One is that apart from long wavelength orientational fluctuations, the nematic phase has topological defects, which in the ordered phase stay nice and bound. Because the nematic is, the molecules are head-tail symmetric and the ordered phase is fore-aft symmetric, those defects are such that if you walk around one of them and you incur a pi rotation, you're back to the same orientation. Okay, so these are called strength half and strength minus half defects. If you walk counterclockwise around this, you go around by minus pi. If you walk counterclockwise around one of these guys, you go around by pi. You can also have integer strength defects. But look at these two guys. There's an important difference between them. Remember, so by the way, the reason this story of defects became important is we were trying to find direct experimental evidence that the mechanism that we talked about back then, 2007, curvature-induced current, was really at work in our system. So we said, let's go after the places where the curvatures are largest. In those places, these guys and these guys both have large curvatures, but the curvatures here have a net polarity. The curvatures here are kind of 3/4 symmetric. So whereas it's true that you will get, so you can imagine that this object should be self-propelled. So we actually argued back then that the symmetry of the field around the plus half defect has a polarity, and so it should follow its nose. We did this, and then we said, let's go look for it. So this three stills show you the plus half defect moving from here to here to here, while the minus half defect stays where it is. And just for fun and completeness, just take a look at that movie. The reason I'm dwelling on this a little bit is, anyway, there it is. You can, if you look with a parent's loving eye, you can see that. There. Okay, so this is really cool. Yeah, it's important because the motility of the plus half defect is quite distinct from a more elaborate hydrodynamic instability mechanism that generates plus half defects that you saw in Zvonimir's movies, where aligned state underwent a bend instability and produced those defects. Here, if any kind of noise produces a plus half defect, that plus half defect is motile. Okay, so the issue that confronted us was the following. You recall again from Hughes' talk, in the context of crystal, he talked about the KTHNY theory of melting. Let's apply that same idea to this system. You've got a system with plus half and minus half defects. If you write down the elastic theory and the fields around these defects, you will find that defects of opposite sign attract each other with a logarithmic potential. So applying essentially the ideas that we've talked about for the equilibrium problem, a 2D nematic should undergo a melting transition by the unbinding of defects once the temperature exceeds some number into the normalized stiffness. Okay. In our system, however, the plus half defect is motile. So if you are a plus half defect sitting on your own, you have, roughly speaking, a constant force acting on you in the direction in which you are pointing. Okay. So that's trouble, because if you think of that, let's imagine a minus half defect just sitting here, and I've got a plus half. So here is a minus half, here is a plus half. This plus half is going to think it's being propelled in that direction. If you think of that in terms of an effective potential, if you think of velocity proportional to force, force is derivative of potential, that's a potential with a minus some number times r. So the effective potential that this particle sees in the presence of a minus, that this plus half sees in the presence of a minus half, grows logarithmic, is logarithmically attractive at short distances and is a minus r at large distances. So if you just take a very naive approach, you've got this plus half and this minus half. If you wait around long enough, they will fly apart, right? Because that you start out somewhere here, that barrier is finite. So that means, does it mean that active nematic order is always destroyed? So what Suraj and, I don't know if I have all the names listed somewhere. Okay, I seem to not have all the names listed. Ah, here. Suraj, Christina, Mark, and me, as it happens, showed is that this picture is naive, and it's naive for the following reason. If you write down the equations of motion for these guys, they attract each other with this potential. They have some noise. The minus half only feels the plus half. The plus half not only has its interaction with the minus, but also has a self-propelling bit. But this self-propelling bit is in a certain direction. And that direction is the direction of this divergence of Q. And that direction, however, has an equation of motion, which is that it has this, through this physics, it has a tendency to align its direction with the direction of the force between the plus and the minus, but with an angular noise. And that angular noise is what can save the nematic phase. Okay? So the idea basically is that this picture is good as long as the noise is low enough that as it starts from here and starts walking towards where it thinks that maximum is to escape, it doesn't lose its way. If it loses its way, that is, if its persistence time is too short, rotational noise saves the nematic phase. So you put these together and you get, roughly speaking, a picture in which, for a given level of activity, if you go to very low noise, because low angular noise means persistent motion of defect, you melt. If you go to very high noise, you melt for the same reason as at equilibrium. And in between, if your activity, if your motility of the defect is not too large, you will have a nematic phase. To date, we don't know that this is really what happens in real active pneumatics. Unless there's been an update on this, no one has seen this in an experiment yet. There isn't exactly a universal phase diagram because there's a certain dimensionless combination of two parameters in the theory. This is Suraj's beautiful effective phase diagram. Okay. This problem, I promised you that I'd tell you history and an update. The update, when I last checked, was beautiful work by Suraj and Christina on defect ordering, which I don't know if they'll talk about, but anyway. All right. So that ends one specific topic. It is fairly clear that I'll only be able to do one more, and I think that's just fine because I'll soon be exhausted. So I'll talk for another 15 minutes? All right. Oh, no, how much time shall I can talk for another 20 odd minutes, right? Yeah, great. Huh? I can, okay. I should stop at 5:10. All right, cool, yeah. Okay, so you may have seen that I showed you experimental measurements on active systems on this funny vibrated surface. So that setup actually is an industrial shaker. It's a big machine. The particles that we're talking about are macroscopic particles, 0.5 centimeter long. And they're placed in a chamber like this. And you shake this thing up and down. And when you shake it up and down, the particle comes down. And if there is any mechanical asymmetry between the two ends, it ends up getting impelled along its length, like this. So I guess I showed you this movie, so I won't show it to you again. Yeah. This idea, in the context of a bolt in a track, was invented by another person in the room, namely Masaki Sano, in work just around the time we were starting to think about these ideas. Anyway, so the idea here is that you take this two-dimensional world of these particles on this vibrating surface, and it's a world which has a sustained input of energy through it. The internal tilt of the particle is like the working coordinate of a motor. Its coupling, that together with its coupling to the base is the analog of the chemo-mechanical coupling that I talked about early in the talk. And these particles will walk if they have a polarity. They'll shuffle back and forth if the two ends are the same. They'll do practically nothing except maybe a little diffusion if they're spherical. Okay? So it's a versatile system. It has one very bad limitation. Physicists like us want to study the thermodynamic limit. Here you're lucky if you can get a factor of 100 between the largest dimension and the smallest dimension. Typically more, like 50 or 30 or something. So that's unfortunate, but it's one of those systems for which you can do larger simulations than experiments, which is a bit embarrassing. Okay, but anyway, let me spend a few minutes on this problem. I don't remember if I showed you this one moving through a... Yeah. So here we have a particle, one motile particle moving through a medium, and that medium consists of little round particles. In these experiments, the round particles are aluminum and the long particle is brass, okay? So let's take a hydrodynamic approach to this problem. Remember, I said that's what we're going to do. We're not going to worry about fine details. We'll take the system and say, okay, I eventually actually want to do something more, something that could potentially reproduce the kinds of results that you talked about. But imagine I just have one active particle. The remaining beads, it's arguable whether the beads are active or passive. It's true the beads are so structureless that even though they represent a system that's being driven, and at each collision energy is dissipated and goes off into the cold emptiness of the universe, a spherical particle doesn't have the wherewithal to do anything with that energy. Maybe more complicated structures like defects could, I don't know. If they weren't even orientable, if they were just disks, they would already be different from spheres. A 2D array of disks could well turn out to be something like the systems that Hugh was talking about, because a disk can be tilted and we'll know that it's tilted. A sphere doesn't know it's tilted. So the equation of motion that one such particle would obey is that it would follow its nose, and the velocity field of the bead medium would get damped by the substrate and by interaction with neighboring particles. It'll get forced by this one moving particle, and maybe there's some pressure from density changes in the beads. The orientation of each of these particles would change because of flows in the medium. Because the whole thing is on a substrate, you don't have to worry about Galilean invariance. You can have terms that are directly proportional to the velocity itself. You can also have reorienting terms that come from velocity gradients, which will rotate and align these particles, okay? And what happens actually is you can do a detailed measurement in a computer recreation of this, and you will find that one moving particle produces two vortices on its side. If you put, and that means that, and the distance out to which this vortex, this flow remains pointing in the same direction as this guy, is larger and larger the more dense you make the beads in the surrounding. So the velocity decays fast in bead diameters if you, excuse me, if the density is lower, and slower as the bead density is made higher and higher, okay? So if you put another particle in it, maybe slightly ahead of or slightly behind, you'll get this aligning interaction. The idea is this: you've got something pointing this way, so it's like this. If a flow comes along like this, just like a weathercock on top of a building pointing in some direction, if you have a wind that comes along, it will turn the weathercock to point in this direction. So this term, orientation parallel to velocity, is just the physics of a weathercock. And you can see that happening. So that's one part of the story. And what you find, I thought I had the other part of the story. No, I guess I have both, yeah. Sorry, both of them are here. So a rod produces a flow that decays, that is roughly in its own direction as a function of distance. Another rod placed in its vicinity is reoriented to point parallel. So you could expect, perhaps, that this system at high enough bead density, even with a very small number of rods, could go into a coherently ordered state. And that turns out to be what happens. I don't know which of these ones, maybe this is the one. No, this. So what you can see is that these guys actually form an ordered phase. They all start going the same way. And you can study a phase diagram in the rod area fraction, bead area fraction plane, and if you go to large enough area fraction, you get ordering. You get other very interesting phenomena over here, which I may talk about in my third lecture if I have a chance. Let's see. And you can measure the amount of order as a function of bead area fraction, and it has a reasonably nice onset. And I already told you the mechanism. Okay, and you can, let me skip over the theory beyond this. Okay, so that's what happens when you have motile. By the way, actually, you can stop me. Do you have any questions at this stage? Back there? Or do you want to ask at the end? I should have told you can stop me anytime you like. Okay. Now, apart from an aligning interaction, what's worth noting is that, my arrows have reversed, I'm sorry. Those heads are supposed to be there, but it doesn't matter. If you've got one of these guys moving on like this, it produces this vortex. If you place another rod by its side, it gets turned. So please allow me, please think of those arrows as being on this side. OpenOffice does strange things sometimes. Like these, I don't know where these came from. They're not supposed to be there. They're only supposed to be those. So,
No, one is larger than the
yeah, luckily it has a net polarity, but it could have been worse. It could have actually cancelled. But this is some weird effect. Anyway, so you place one of these guys that's moving along like this, and you put another one near it, it turns away. So if you think of this, there are in biology various kinds of taxis phenomenon, which has to do with things reorienting to point towards and move towards or away from something. It looks like if they're placed side by side, there's an effective repulsion, and that effective repulsion is not that the centers of mass are pushed away directly, but that they are self-propelled and their direction of motion is turned by the gradient. So in the fluid medium, these flows mean that if you have got two particles, they tend to turn away from each other. So now you take this same system, start increasing the coverage by beads. And what happens is the bead area fraction builds up. You can more or less see the sort of classic liquid hexatic crystal by looking at the bond order parameter, using long-range six-fold order as a proxy for quasi-long-range crystalline order. Okay, you can do better than that. You can measure the elasticity effectively by taking one particle and constructing an object by measuring the mean square displacement of the object and doing what is called bead microrheology. You construct an object which will approach a non-zero value at low Laplace frequency if you carry out this particular procedure. It's very straightforward. It's just saying that you take one particle. If it ends up being more or less permanently caged in its surroundings, you say, that's a solid. If it diffuses far away, you say that's a liquid. You can do better than that. It's good enough for our purposes. And as a function of bead area fraction, you can see that there is not a beautiful, but sort of acceptable onset of a non-zero value for this quantity. So as a function of bead area fraction, this system goes from fluid to crystalline. And by careful measurements, you can see that it also goes through hexatic, but that's not an issue of interest to today's lecture. And you can see what happens to the excuse me. If you look at one particle, and this is a computer recreation. If you label a set of particles in some color and look at what one particle does, it escapes. It doesn't drag those guys with it, right? It leaves the medium unaltered. Whereas if the medium was fluid, it drags the particles with it. Okay, and so the question is, what does this actually do to the medium? It clearly doesn't produce flows. In the fluid medium, it produces flows. In the crystalline medium, it produces no flows. And so you can then go back and say, okay, now I'm going to write down equations of motion of the sort that you wrote down for the medium. Okay, and I have only one particle right now at this level of analysis. This guy is in fact the thing which, if I had many of, would produce a local colored noise. Yes? Yeah. Right.
But previously you showed that,
Yeah, it's on now.
it's on, okay. So previously you showed that the extent to which the vortices extend, that length scale increased with the density.
So it's just like always happens when you go from a fluid to a solid, right? Actually,
So
you sort of get a correlation a dynamical correlation scale that gets bigger and bigger, and then eventually gets frozen out.
Okay.
So it's that odd fact. Yeah.
Okay.
Yeah. So so this is our very elementary equation of motion for this system. So this is the dynamics of one particle here, not worrying about any other effects. This is the dynamics of the medium forced by one single agent. And this is the dynamics of the orientation of that one single agent in the presence of not the flow field, but the elastic strain field of the medium. Okay, so you can align either by uniaxial extension, along the extensional axis, or you can align along the curvature of the crystal planes. So these are the two effects that you can have, and you can then work out what this system does. And really, rather than doing it for many particles and working out the phase diagram, we're just asking for what one particle does and how two particles interact as a result of that. Okay, and you can work that out if you just take one particle. If you don't worry about the fact that the particle has preferred directions in which it will move, because this is a crystalline medium, just co-move with that particle. The time derivative becomes a directional derivative in the frame of the particle, right? And so you have two. This is the dynamical piece, this is the elastic piece, and this is the forcing. You've now you're moving with that motile particle, so it's a delta function always at the origin in a fixed direction x. This is a directional derivative along x, and you get a displacement field that decays if you just work out the asymptotics of these modified Bessels. It decays very fast in front of the particle and very slowly behind the particle. Decays because there are two dynamical sort of screening lengths here, coming from the ratio of elastic constants to mean drag force. Okay. Remember, this is yes, it's 2 dimensions. So elastic constants have units of force per unit length. So force per unit length over a force over a force per unit length is I'm slightly bothered now. I think, and those phenomena turn up in living matter context is reassuring, and it's reason to justify this approach to the physics of living and related matter. Thank you.
Questions? There's one at the back.
Hello.
Yeah.
Sir, I have a naive question. So you showed the potential between two active defects has a logarithmic part and V minus mu of R types of part.
Right.
So if I understand correctly, the second part comes due to the activity.
Yeah, the second part is it's a slight cheat to describe it as a potential between those two defects. It's actually trying to represent the fact that that particle, that the plus half defect on its own is propelled for reasons having to do with the active forces in the problem. And that being propelled at a constant speed in a damped system can be viewed as being propelled by a constant force times a mobility. And a constant force is like a linear potential. A constant force pushing in some direction is a forever decreasing potential in that direction. So it's convenient at this 2 defect level to write it that way.
So you said that this type of thinking in the sense of theoretical formulation also applies to a very small object like a cell.
Remember, a cell is not very small. A cell is many microns in size. A perfectly good hydrodynamic description applies to the interior of the cell. These guys wrote down the hydrodynamic equations governing the cytoplasm and cytoskeleton, which is stuff inside a cell. That's lots of microns. It's much bigger than the Planck scale.
I was just wondering about whether
really,
even thermodynamics or ordinary statistical physics will apply.
Yeah, absolutely. Because
it's not so small.
It's not so small. I mean, think about the typical computer simulation of a liquid, right? So, but the beauty is, it turns out that you can get a lot of the truth of what goes on inside a cell with this level of analysis. Even though the inside of a cell is complicated in another way, it's heterogeneous, many things going on. Even then, it turns out coherent. I didn't talk about it. I'll talk about it next week. The instability of the aligned state and the resulting spontaneous flow and so forth, all of that actually manifests itself inside a cell. And many experiments ranging from inside a cell to whole cell layers have seen it. Yeah, so...
but it works even better for tissues.
It works great for tissues, but what's... Yeah, so...
The most dangerous tumors are nematic.
Right. Yeah.
So, when you are talking about this movement of the particle through this medium, which is either fluid or crystal,
yeah.
When it is crystalline, there is no, I mean, it's not dragging the fluid.
Yeah.
But in the crystalline phase, you can also have long-range states sort of...
The strain fields are exactly the thing that came into the analysis. That's what we wrote down, right? We wrote an equation for the displacement field. I wrote down an equation of motion for the fluid medium, where I think I tried to use different symbols. I think I called one of them V and one of them U, but I'm not sure. The equation, the hydrodynamic description of the crystal was for the dynamics of this displacement field. And so the moving particle produces a strain field, which is a stationary strain field if you co-move with the particle. If you have many particles, then everything is dynamical, and you have to keep track of the dynamics. So we just did some easy things like 1 particle, 2 particle.
And when you have the fluid, is it matter of time scale? Like if the particle is moving really fast, will you still have to include the displacement field, or you can still ignore in that case?
No, in the fluid, there's no displacement field. So you could ask about a viscoelastic fluid, for instance. So these guys, in the Madan and company, in the viscoelastic system, just use the density. They didn't really use you didn't use a sort of long-lived strain field. You could imagine doing various, patchworks of the two, but they didn't do that. Yeah.
Questions?
Just curious what you meant by zero Reynolds number terminus.
Okay, the point is, all
it's
of
just
these,
like a couple of minutes.
yeah, so that will, I'll discuss it briefly at the beginning of next talk. The state that Rahul talked about, active turbulence, or that Zvonimir showed a little bit in his those filaments thing. The idea is the following: so that was supposed to be the end of this talk, but still, the idea is you take an aligned state. I mean, if you like, I can just show you that slide. That's the easiest thing to do. I think I have it here. Yeah, I think yeah, so the way to analyze a collection, imagine you've got a bunch of swimmers like this. Each of them is characterized by an orientation, which I'll call P. I mean, let's let P be the collective orientation vector field. So this is a co-moving, co-rotating derivative. In principle, you should allow P, the P field, to advect itself also, because it's a velocity also, right? So all that I've buried in here. Here, this thing is the piece that just says that if I impose an extensional flow, then this being an orientable object, it'll have a tendency to line up with that flow. And then imagine that these guys have some interaction governed by some, for want of a better idea, some free energy functional, which aligns them, and maybe in the absence of all these activity and flow and all that, produces some ordered state. Now you ask, what happens if these guys carry little swimming stresses? Okay, this guy swims like this, that means it pulls fluid towards itself, moves forward. Those stresses will go into the equation of motion for the hydrodynamic velocity field. Now, over the length scales of interest to these kinds of experiments, you can completely forget the inertia of the fluid. Okay, you work in this regime, which is just like Newtonian gravity. You tell me, so except Newtonian gravity, you describe the matter distribution, you calculate the force. Here, you describe the force density, and you calculate the velocity, because you're solving Newton's law here, and the sources are the sources that produce flow. So you specify the force densities everywhere, and Navier-Stokes equation tells you how to evolve the velocities forward. It turns out to be completely okay to say that force densities everywhere define the velocity fields everywhere instantaneously. Okay, the mistake you're making, I mean, in principle, you're making two mistakes. The fact that there has to be a finite speed of propagation even in a viscous fluid, that's one mistake. But that's the mistake, that has to do with incompressibility. The other is you're pretending the viscosity is so big that over all the time scales you're looking at, all the processes you're interested in take place much slower than the viscous diffusion time it takes for the velocity to know everywhere what the forces are. Okay, that time is on a length scale. L if the fluid has a mass density rho and a shear viscosity mu, then that time on a scale L is right? Velocity gradients diffuse with the diffusion coefficient equal to the kinematic viscosity, which is viscosity over mass density. You're basically ignoring effects having to do with the inertial mass. So this time becomes 0. And it's pretty good. You can put in numbers. Another way of asking is that, I mean, you can put in numbers and ask how big a system has to be before this process becomes important. For example, if you've got swimming bacteria, and they're run and tumble bacteria, they go straight for about 1 second. What that means is that corresponds to a length scale in water of about 1 millimeter. So it's sort of on the edge, but for a reasonable range of length scales, it's still okay. And very often, even if the processes do involve some diffusive time of propagation, it still doesn't matter. You can get away with it. So what this means, therefore, is that it's like treating, remember the Reynolds number, if you've got an object of some size L moving with some speed v, then you can, the one time is L over v, the other time is this time. This is the time it takes velocities to even out on the scale of this guy, right? This is the time it takes the particle to move its own length. And you can compare those two, and the ratio of this over that, this divided by that, is, and if you evaluate this for a bacterium of some 20 micron in size, moving at some 10 microns per second or something, it's I don't know, it's 10 to the minus 5 or something like that, right? Yeah. Yeah, so the point is, so we're working essentially at 0 Reynolds number. We're forgetting inertia here completely. The aligned state, it turns out, if you consider an aligned state and perturb it slightly, this is the stuff that Zvonimir talked about, same cartoon actually. If you perturb it slightly, then if you have swimmers of this sort, then you can sort of see that they're pulling the fluid more from here than from here. And here they'll be pulling the fluid down more from here than from here because these bits are sort of closer together, farther apart. So this perturbed state will further get perturbed in the same direction. If instead they're pushers, then you can use the same analysis and see that you will get this kind of instability. The end state, and all of this will happen on a big enough scale because you'll get competition from liquid crystalline elasticity in principle if it's there at smaller scales. The point is that the weird thing is that this is an effect with a single growth rate on long length scales. Okay, stress divided by viscosity divided by stress has units of length, and within this 0 Reynolds number limit, that length scale is the length scale associated with any competition between viscosity and stress, irrespective of length. Okay, this sort of the instantaneous. It's one of these things that weird infrared things that happens when you have a long range force. Here it's the Stokesian hydrodynamic long range force, right? So on big length scales, you have this growth rate. On smaller length scales, elasticity can be important. But basically, if you let this instability happen and you let it go, it results in a state where the alignment is completely disrupted and the fluid flow is chaotic. Okay? It's chaotic, and on length scales big compared to that internal length, it has within the Stokes limit where you ignore inertia, it has a 1 over r to the d minus 2, or a 1 over r decay in 3 dimensions. So it's correlated but random. And that state is turbulent, and it's obtained not by a competition between inertia and something else. In my second lecture, I'll tell you about what inertia does to all this a little bit. But it's all about the competition is between liquid crystal elasticity trying to fix things. So you have the competition is between liquid crystal elasticity trying to relax things. So if this is a Frank orientation elastic constant, viscosity and wave number, this is one relaxation rate versus the active stress divided by viscosity. So you can see really the viscosity drops out of it, and you have a characteristic length scale. On scales bigger than root of k over sigma a, it's just utterly unstable. It's sort of incurably unstable as long as you ignore inertia. Of course, the truth of the matter is there's something much cooler that happens here, and that you have to read about in Ananya's paper or hear about in Ananya's talk. Yeah. Okay, so that's zero-Reynolds number turbulence.
The questions? Okay, so if not, let's thank Sriram for a wonderful talk.